previous lectures, we saw how we apply the concept of angular momentum to solve rigid body problems, and we mainly focused on conservation of angular momentum for bodies moving about a fixed axis. In this lecture, we are going to start with the motion when an external torque on a body is applied. For example, let me show you. I will take this scale and hold it on a horizontal position like this and leave it. Take on the horizontal position and leave it. What I would like to know is, when it reaches here, ignoring friction, what is its angular speed? So, the problem that I am solving is, I have a scale like this. It can rotate about this point O, for example, and when we leave it, it drops down like this. And I would like to know what is its angular speed omega when it comes here. I will solve this problem in two ways, show you what a wrong way. So, let the length of the scale be L, so that its center of mass is at L by 2 if it is a uniform scale. Let its mass be m. So, first let me apply energy conservation right away. When the scale falls, its center of mass drops down by a height of L by 2. So, the energy gained should be equal to m g L divided by 2, and all of this energy gets transformed into its kinetic energy, which in this case is the rotational kinetic energy about point O. This is point O, I remind you, and this is going to be equal to 1/2 I about point O, which we have seen in the previous lecture is ml square over 3 times omega square. The two should be equal, and therefore, I have 1/2 m L square over 3 omega square is equal to m g L divided by 2. This m cancels, this 2 cancels, one of the L's cancels, and therefore, I get omega equals 3 g over L square root. So, this is the answer that comes from energy conservation. Second way is by applying the equation that dl dt is equal to external torque, and let us apply that. Let the position of the rod be at an angle phi from the horizontal. At that point, all the force acts here mg, and therefore, the torque that is being applied is going to be equal to mg L divided by 2 cosine of phi, because this distance is L over 2 cosine of phi, and this should be equal to dl dt, which is nothing but I about point O d omega dt, and therefore, I should have I, which is the moment of inertia, d omega over dt is equal to mg L divided by 2 cosine of phi. As I already have mentioned, I is m L square over 3, omega is d phi over dt, and therefore, d omega over dt is d2 phi over dt square, and therefore, the equation when the rod is at an angle phi from the horizontal is going to be m L square over 3 d2 phi over dt square, which is I alpha or I times the angular acceleration, is equal to m g L over 2 cosine of phi. L cancels, m cancels, and therefore, I get L over 3 d2 phi over dt square is equal to g over 2 cosine of phi. Since the left hand side involves t, we will use an old trick that we have used earlier in deriving energy conservation, and that is to write d2 phi over dt square as d over dt of d phi over dt, which is nothing but d over d phi of d phi over dt times d phi over dt, which can be written as 1/2 of d over d phi of phi dot, which is d phi over dt square, and therefore, the earlier equation becomes 1/2 d over d phi phi dot square, which is nothing but d2 phi over dt square, is equal to m g L over 2 cosine phi, and there was an I here, which is m L square over 3. I had simplified it earlier, I will do it again. The m cancels, this 2 cancels, one of the L's cancels, and therefore, I get d over d phi of phi dot square is equal to 3 g cosine of phi, and therefore, integrating, which is d phi phi dot square equals 3 g cosine of phi. There is an L also here, which I can write L here. This is for a rod which is of length L, and this angle is phi, and this gives you L phi dot square is equal to 3 g sine of phi starting from 0 to angle pi by 2 when it comes to the vertical, and this gives you phi dot square equals 3 g over L, which is the same answer as obtained earlier. So, I have used energy conservation directly, and I have also integrated the equation of motion, which essentially by this transformation comes to energy conservation along, energy conservation by itself. Now, you may ask at this point, why did not I do one more thing? Why could not I do that 1/2 m v center of mass square is equal to m g L by 2 when the rod came from here to here? After all, it is the center of mass which is moving, and it moves with a speed v c m, and this should be equal to the gain energy because of the potential energy drop. What is wrong with this? What is wrong here is that you have to be careful when there are extended bodies involved, when velocities are distributed over the body, when forces are distributed over the body, that what all is happening. For example, here if I start with this position, here is the center of mass. When the rod comes in this position, not only has the center of mass moved, you see with respect to the center of mass, the body has also rotated like this. So, in coming down like this, the scale is performing two motions. The center of mass is moving, and the scale, as you can see, is changing its orientation with respect to an axis passing through the center of mass. It is rotating, and it is rotating exactly by the same angle as it was rotating about O. So, actually the motion is 1/2 v c m square plus rotation about c m, and if you calculate the kinetic energy, it is always K E of c m plus K E about c m. It will come out to be 1/2 mvcm square plus 1/2 I about cm, which will be ml square over 3 omega square. Omega by definition here is going to be vcm divided by L by 2, which is 2 vcm divided by L, oh sorry, about center of mass, this should be 12, not 3. It is 3 about the point O, about cm it is 12. If you substitute these numbers in, you get precisely the answer that you got earlier. What you may ask at this point is, but what about the torque? Torque, the forces are also distributed, but I took torque to be acting at the cm. Because the torque depends linearly on the distance from the pivot point, its average comes out to be as if it is acting on the center of mass, but not when I calculate the moment of the velocity, because that becomes r times r omega. It depends on it as r square. So you have to be careful when we are talking about rigid bodies and distribution of forces and velocities over the body, that we take proper consideration of rotation and angular momentum also. As an extended example of this, let me now take this booklet. I'll keep its printed side on top and drop it. I'll keep the printed side on top and drop it. You see, the printed side has gone down. Let me do it again. I'm keeping the printed side up, dropping it roughly from 1 meter, and let's see what happens. The printed side goes down. Can I explain this? In fact, there's a very famous book based on such a thing. The book is known as Why the Toast Lands Jelly Side Down. It has been generally observed, if you are applying jam or butter or jelly on your toast, if it drops from your hand, roughly the jelly side always goes down. Let us try to understand this using our rotational dynamics. So roughly, I'll take this book, which is, let's say, of the order of magnitude about 20 or 15 centimeters wide, and I was holding it here. What it did was, first it went down like this, it rotated about this point until it reached an angle when it slipped off. Once it slips off, it starts falling down, and when falling down, it rotates. What we observed, it rotates roughly by 180 degrees. Why roughly? Even if it is 150, it will fall down the other side down. Even if it is 200, it will fall down the other side down. So let us try to understand this. First step is, when the booklet is like this, let the length, the distance of the center of mass from the pivot point, or where I am holding it, be L. Then it experiences a force mg at the center of mass and a torque mgl, and therefore it should have an angular acceleration which will be 1/2, which will be I times alpha. Alpha would be equal to mgl divided by I, which is ml square over 3. 1l drops out, m drops out. So the angular acceleration is roughly 3g over L. It covers an angle theta, which will be equal to 1/2 alpha tau square, where let me write tau as the time when it slips from the hand. So theta is roughly alpha tau square. What should be the value of theta? We know from mechanics that if a body is at an angle such that this is theta, this is mg, theta 90, this is 90 minus theta. This force would be mg sin theta, this force component would be mg cosine theta. So, if mg sin theta roughly becomes mu times mg cosine theta, then the body is going to slip off my hand, and therefore, I can write tangent theta roughly equal to theta for theta small equals mu. So, when mu equals 1/2 alpha tau square, this booklet is going to slip off. Let us take a typical value, mu equals roughly 0.2, alpha is given to be 3g over L, which I will take to be roughly equal to 3 times 10 over 0.1 meters. So, that comes out to be roughly 300, and therefore, I have mu which is equal to 1/2 alpha t square, 0.2 equals 300 divided by 2 tau square, or tau, the time for it to slip off is going to be 0.4 over 300, roughly 1 over 750 tau square, and therefore, tau equals 1 over 750, which I can write as maximum 1 over 30 seconds. So, we have come up to the point where the toast or this booklet came here and slipped off. This time tau is roughly 1 over 30 seconds. In this time, it has gained an omega, which is alpha tau, and after it slips off, that omega remains a constant and makes it rotate. So, this is roughly equal to 1 over 30 times 300, which is equal to 10 radians per second. If this dropped by 1 meter, then the time taken for it to drop would be given by 1/2 gt square equals 1, t equals 2 over 10 square root, which is roughly 1 over 2.5 seconds. And therefore, you see that the angle by the time it comes down would be equal to omega times t, which is 10 times 1 over 2.5, which is 4 radians. That is slightly greater than 180. So, that is roughly the angle through which the book rotates, and you see it drops the other way. This is an interesting problem where we applied the ideas learnt so far. Having done the problem where the axis was fixed, let us now move on to problems where if I am given a rigid body and I hit it with a force, its center of mass could move according to dP Cm divided by dt equals force external, but also because the forces are distributed over the body itself could change orientation as it moves. For simplicity to start with, we will be confined with motion where axis moves only parallel to itself. For example, it could be a rod on a horizontal table being hit by a force here, then the axis would move parallel to itself, the axis would be perpendicular to the table, and also the axis moves with constant speed or could accelerate. We want to see how to describe the motion of the rigid body in this case. So, let us take a rigid body, apply say force here. One thing is very clear, that the center of mass moves according to this equation that we had already derived. What about the torque? There is a torque about any given point which is not in line of the force, and this should be equal to d L dt about that point. Let us call this point O. Could O be any point? Should O be Cm? Should O be a particular point specified by certain conditions? We do not know, but we do wish to apply this equation to describe its orientation change. This equation we know for sure describes the motion of the center of mass. Usually you must have seen in your 12th grade or so that O is taken to be the point center of mass, but why? That is the question, and that is what we wish to answer now. Remember, our goal is to apply dl over dt equals tau only external when a body is moving. So, let us take a general point O and a body that is being applied by several forces, and let us calculate the angular momentum L about O. This by definition is going to be summation m I r I with respect to O cross V I with respect to O, where I is some general point, and therefore, d L O dt, and so far we have been doing that when we take the first derivative dr over dt, that gives you 0 when crossed with velocity. So, it comes out to be summation m I r I with respect to O cross d V I O over dt. Let me show you, this is r I O, this is r I, that is the coordinate of the point with respect to an outside origin, and this is r O. Now, V I with respect to O is nothing but velocity of ith point with respect to outside point minus velocity of O, and therefore, d V I O over dt is going to be equal to d V I over dt with respect to outside point minus d V O over dt, and therefore, we get d L O over dt, that is the rate of change of angular momentum with respect to point O is equal to summation I m I r I O d V I over dt minus d V O over dt, and I have forgotten to put a cross sign here. Let me remind you again, this is my reference frame, this is my body, this is point I, this is some arbitrary point O, this is R O whose derivative gives me V O, this is R I, and this is R I O. dVi dt is equal to acceleration of point I with respect to the outside point, which is an inertial point, and therefore, m I times this is f I external, and therefore, I can write d L O over dt is equal to summation r I O cross f I external minus summation m I RIO cross, this is nothing but the acceleration of point O, acceleration of point O. So, what we have obtained now is that the rate of change of angular momentum when angular momentum is taken about an arbitrary point O, which could be in the body, which could be accelerating or anything, is equal to summation I RIO cross Fi external only minus summation I Mi RIO cross acceleration of point O itself. This by definition is the external torque with respect to point O, no matter what the point O is doing. So, this is tau external with respect to point O minus AO is a constant as far as summation over I is concerned, and this is nothing but m times R of Cm with respect to O. So, if I want that dl dt be equal to this only, this term must vanish. Let me remind you again what we are doing. What we are doing is we are taking a rigid body, taking an arbitrary point O on this, applying some force on the rigid body, calculating the torque due to this force with respect to point O. Point O could be accelerating, moving, whatever, and then when I analyze this, what I find is that dl O dt is equal to tau external minus m R of Cm with respect to O cross acceleration of O, and I want this term to be 0. I want to choose this point O in such a manner that the last term vanishes, so that with my eyes closed I can always apply dl over dt equals tau external only. This would vanish under three conditions. Number 1, R Cm O itself is 0, and that would be the case if O, the point itself, is center of mass. And this is what you have been doing in your 12th grade or whatever, that you have been taking talks about center of mass and have been applying dl about Cm divided by dt is equal to tau external about the Cm, or this should be about O. Number 2, acceleration of point O itself be 0. That means O is moving uniformly. And third, that acceleration O be parallel to RCM O. That is, the point O is accelerating towards the Cm itself. This also you have been doing in your 12th grade. For example, in a wheel which is rolling, you usually take torque about this point and apply dl dt equals tau. This point is actually accelerating towards the Cm, and therefore your answers come out to be correct. So, there are only 3 points in a body in which case this term vanishes, and I can apply with my eyes closed that dl O dt is equal to tau external about that point. We will take a few examples using this equation. So, what we have learned in general, and so far I am restricting myself to only that motion in which the axis moves parallel to itself, that d L about Cm dt is equal to tau external only, no other forces need to be taken into account, no pseudo forces or anything can be applied safely, and the motion of the center of mass itself is given by d Pcm over dt is equal to F external. These two equations are sufficient to describe the entire motion of the body, in that how it is translating, that is given by this, and how it is changing its orientation is given by this. As a first simple example of this, let us take a rod uniform of length L, and let us hit here with an impulse J. Impulse, as you would recall, is nothing but integral f dt, where f is applied for a very short time. So, this is a very short time delta tau, let us say. By the momentum equation, you get that the momentum gained by the rod should be equal to PCM equals J, and therefore, M V Cm should be equal to J. So, after the rod is hit, its center of mass should move with this velocity. How about the omega that it obtains? As we have already seen, I can safely write, let me do it right here, that the angular momentum it obtains about the center of mass should be equal to the impulse, torque impulse that it gains about the center of mass, and that will be J L over 2. And therefore, M L square over 12 times omega should be equal to J L over 2, and it ends up getting omega equals J over M L times 6. So, it rotates as it moves with this angular speed, and it moves with this center of mass moves with this speed. Let us take another example. Let us say there is a wheel which is thrown this way with a velocity v, and it is moving on a smooth surface. There is no friction here. Suddenly, it encounters a rough surface. The surface is so rough that it starts rolling right away. So, here it was just moving, there was no rotation, there is no rotation of the wheel about the center of mass, and as soon as it hit this rough place, it started rotating, rolling, so that its lowest point was stationary at that point. What about its rolling speed? So, let us see what has happened. The moment it hits this rough patch, it gets an impulse J in this direction. Initially, if it was moving with momentum V, this momentum now gets reduced because of this impulse. So, that comes from momentum equation. Not only that, if it is rolling, then it should also be rotating about the center of mass with the speed v1 over r, and therefore, it has gained an angular momentum about the center of mass. Where does this angular momentum come from? That angular momentum comes from the impulse that it got here. So, the torque impulse it got is equal to J times r with respect to center of mass. So, the angular momentum it should obtain about the center of mass should be equal to J times r, and this tells you I is m r square, omega is equal to J times r, r cancels, r times omega is v1. So, m v1 equals J, and therefore, putting this in this equation, I get m v minus m v1 equals m v1, or v1 equals v over 2. So, as soon as this wheel which is moving with speed v without rolling on a smooth surface hits a rough surface here, it will start rolling with speed v over 2. As a third example, let me take a rod, and you must have seen this if you sometimes drop things. Let its initial angle from the horizontal be phi, and let its height from the ground be h, and let it drop. You must have seen it happen at home. If you drop something like this, it goes back and forth, and you hear a voice tuck 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 tuck. So, what I want to know is, after it hits the floor and suppose no energy is lost, what will be its rebound velocity? and what will be its rebound omega. When it drops from a height h, when it reaches here, its velocity is going to be the square root of 2 g h. So, and when it hits here, there is an impulse that acts here, let that be called j. So, I am going to have square root of 2 g h times the mass of the rod minus m v, this is the loss in the momentum, that should be due to j. That is from momentum equation. Similarly, now I apply the torque equation about the center of mass, which is again the safest point to apply it from. This j gives you a torque impulse. This distance is going to be L over 2 cosine of phi if the length of the rod is L, and therefore torque impulse is going to be j L divided by 2 cosine of phi, and this must give it an angular momentum about the center of mass I omega, or m L square over 12 omega is equal to j L over 2 cosine of phi. That is equation number 2. I have 3 unknowns, v, omega and j. So, I need one more equation, and that comes from energy conservation. The energy conservation tells me that the energy that it gained while being dropped, the kinetic energy it gained is going to be equal to mgh, and that should be equal to its energy right after rebound, and that is going to be 1/2 m v square plus 1/2 I omega square, which is equal to 1/2 m v square plus 1/2 ml square over 12 omega square. M cancels, and therefore you get 2 g h equals v square plus L square omega square over 12. So, now I have got 3 equations to solve to get my answers. The 3 equations are m square root of 2 g h minus m v equals j. Then I have ml square over 12 omega equals j L over 2 cosine of phi, and third equation I have is 2 g h is equal to v square plus L square over 12 omega square. Substituting things properly, I can get my answers from this, and this I will leave as an exercise for you to solve. As the last example I take is a very interesting one and a very famous one. It is, if I have a ladder leaning against a wall and on the floor here, and suppose there is no friction, then the ladder obviously would start slipping like this. The question is, if initially it was at height h, at what height does the upper end of the ladder leave the wall? If I make a free body diagram for the ladder, there is going to be a reaction N1 here and N2 here. The point at which N2 vanishes is going to be the point where the upper end has left the wall. So, what we want to determine is N2 and make it 0 to find this out. Let us see what is happening as the ladder comes down. As the ladder comes down, its center of mass has moved down. Not only that, the ladder has rotated about the center of mass. So, it has both a translational as well as a rotational motion. However, all I need to describe its complete motion is this angle it makes with the floor, because the center of mass of the ladder is going to be given by this itself. So, let us make this picture again. Here is the ladder of length L. If this angle is theta, center of mass is right here, you can see that x cm is going to be L over 2. This is x cm, L over 2 cosine of theta, and y of center of mass is going to be L over 2 sine of theta. So, for this ladder I have x cm is equal to L over 2 cosine of theta, and y cm is equal to L over 2 sine of theta. This is n1, this is n2. How about equations of motion? The mass of the ladder times x cm double dot is obviously going to be n2. This is x direction, this is y direction. Mass of the ladder y cm double dot is going to be equal to n1 minus mg. That is for the translation of this center of mass. Equation 1, equation 2. On the other hand, it also rotates as it moves, and it is rotating like this. For the rotational motion, n1, n2, since we are taking theta like this, we will write the equation that way. I am going to have I theta double dot about the center of mass is going to be equal to n2 times this distance, which is L over 2 sine theta, minus n1 L over 2 cosine of theta. This is my equation number 3. So, I have 3 equations, but unknowns seem to be more: x cm, y cm, theta, n1 and n2. However, x cm and y cm are not independent, because as we saw, x cm is equal to L over 2 cosine of theta, and y cm is equal to L over 2 sine of theta. Let us now write expressions for n1 and n2. Let me just make sure that n1 and n2 are the ones that I am taking. X cm is equal to L over 2 cosine of theta, and therefore x cm dot is equal to minus L over 2 sine theta theta dot, and therefore x cm double dot is equal to minus L over 2 sine theta theta double dot minus L over 2 cosine theta theta dot square. Similarly, let us derive y cm double dot. Y cm is equal to L over 2 sine theta, and therefore y cm dot is equal to L over 2 cosine of theta theta dot, and y cm double dot is equal to L over 2 cosine of theta theta double dot minus L over 2 sine theta theta dot square. And therefore, we can write expressions for n1 and n2. n2 would be equal to m times x cm double dot, which is m minus L over 2 sine theta theta double dot minus L over 2 cosine theta theta dot square, and n1 would be equal to mg plus mycm double dot, which gives me mg plus m L over 2 cosine theta theta double dot minus L over 2 sin theta theta dot square. Let us see if I substitute for y theta double dot correctly, y cm double dot correctly, and I did. So, these are equations that give me n1 and n2. Similarly, I theta double dot is equal to n2 L over 2 sin theta minus n1 L over 2 cosine theta, as we wrote earlier. Let us check that. I theta double dot is n2 L over 2 sin theta minus n1 L over 2 cosine theta. Now, if I substitute for n1 and n2 here, let us see what do we get. We get I theta double dot is equal to L over 2 sin theta, n2 is minus m L over 2 sin theta theta double dot minus m L over 2 cosine theta theta dot square plus mg plus ml over 2 cosine theta theta double dot minus ml over 2 sin theta theta dot square times minus L over 2 cosine of theta. Let us see what do we get when we add these two. So, on the left hand side I get ml square over 12 theta double dot is equal to minus mgl over 2 cosine of theta, that takes care of this term. Then I am going to have minus ml square by 4 cosine square theta coming from here minus ml square by 4 sine square theta coming from here, that will give me minus m L square over 4 theta double dot, that takes care of this term and this term, and finally I am going to have plus ml square by 4 sin theta cosine theta theta dot square from here and plus ml square by 4 sin theta cosine theta theta dot square from here. So, that term cancels. So, this is my final equation. When I substitute for n1 and n2 into the equation for torque, if I take this over to the other side, I am going to get m L square over 12 plus m L square over 4 theta double dot is equal to minus mg L over 2 cosine of theta. Let us check that, if that is correct, and that is correct. This is ml square over 3 theta double dot is equal to minus mgl over 2 cosine of theta. I want to integrate this equation, and therefore, I am going to write theta double dot as equal to d over d theta of theta dot square over 2, and therefore, this equation becomes 1/2 ml square over 3 d over d theta theta dot square is equal to minus mgl over 2 cosine of theta, and that this 2 cancels, and that gives me ml square over 3 theta dot square is equal to minus mgl cosine theta d theta is starting from the initial angle theta 0 to some angle theta, and that is mgl sine theta 0 minus sine theta. This is the final equation that I get. A note here, this is really nothing but the energy conservation equation. I would leave it for you to find out that the change in PE of the ladder is equal to the KE of the ladder, which is equal to KE of Cm plus KE about Cm would directly lead you to this equation, but I wanted to derive this equation using equations of motion. Nonetheless, this equation is now the equation that would lead to the answer. So, please try this, that derive this directly from the energy conservation equation. This divided by 2 would give you the change in the potential energy, and these two terms together would give you this term. So, I have ml square over 3 theta dot square is equal to mgl sine theta 0 minus sine theta. So, I get the value of theta dot square. Similarly, I already have mg, the value for theta double dot, and if I substitute these in the value for n2, I will get an expression for n2. Let us go to the expression for n2. n2 was equal to minus ml over 2 sine theta theta double dot minus ml over 2 cosine theta theta dot square, and let us substitute. Let us cancel this, let us cancel m, and this gives me theta dot square is equal to 3g over L sine theta 0 minus sine theta. Similarly, the equation for theta double dot, which we had derived earlier, this one, ml square over 3 theta double dot equals minus mg L over 2 cosine theta. Let us write that ml square over 3 theta double dot is equal to minus mg L over 2 cos theta. Let me make sure this is the equation. ml square over 3 theta minus mg L over 2 cosine theta gives me, m cancels, gives me theta double dot is equal to minus 3 divided by 2 g over L cosine of theta. Substituting these in the expression for n2 here, we get n2 is equal to minus ml over 2 sine theta, and let me substitute for theta double dot, which is minus 3 over 2 g over L cosine of theta, and the next term is minus ml over 2 cosine theta minus ml over 2 cosine of theta, and for theta dot square I get 3g over L sine theta 0 minus sine theta, 3g over L sine theta 0 minus sine theta. So, this gives me minus 3, this L cancels, 3 over minus minus plus 3 over 4 m g cos theta sin theta minus this L also cancels 3 over 2 mg cos theta sin theta 0 minus minus plus 3 over 2 mg cos theta sin theta. Let us add all of them together and we get N2 is equal to minus 3 over 2 mg cosine theta sin theta 0 plus 3 over 4 plus 3 over 2 is 9/4 mg cosine theta sin theta, and the point where the ladder leaves the wall N2 is 0, and this gives me 3 over 2 sin theta 0 is equal to 9 over 4 sin theta or sin theta equals 2/3 sin theta 0. So, if we start with an angle theta 0 at sin theta equals 2/3 sin theta 0, the ladder would leave the wall. So, let us see the picture again. This is theta 0 at 2/3 of sin theta 0, that means that the height 2/3 of the original height, the wall and ladder would separate. So, sin theta equals 2/3 sin theta 0, or L sin theta is equal to 2/3 L sin theta 0. L sin theta 0 is the initial height, this is the height at which the ladder leaves the wall. So, H equals at 2/3 the original height the wall leaves, wall and ladder separate. So, this is another example of how the combination of translational and rotational motion can be solved. So, what we have done in this lecture so far is considered various applications of the equation dl over dt equals tau external. In those problems where the axis of rotation remains fixed or it translates parallel to itself, in that case we saw that we apply d LO over dt is equal to tau external, where O is either the CM or a uniformly moving point, or accelerating towards CM. The safest point to take always is CM, because that you are sure of, and with these we solved certain interesting problems. You can keep making problems more complicated, but the application remains basically of these equations. What I would urge you now is apply these to as many difficult problems as you can. Good reference books to find such problems are Merriam Dynamics and Kleppner and Kolenkov Introduction to Mechanics.